Welcome everyone to The Explainer. I am absolutely thrilled to have you here today because we are about to uncover the hidden engineering marvels behind modern high-speed rail. We're going under the hood, so to speak, to explore the rolling stock, the intense applied physics that keep these machines on the track, and the incredible operational constraints engineers have to overcome. I mean, think about it. A train traveling at 300 kilometers per hour? It's not just a vehicle anymore. It's essentially a low-flying aircraft bound to the earth by steel rails. It is a constant, ongoing battle against gravity, air resistance, and nature itself.
Here is our roadmap for today. First up, we'll look at the global high-speed fleet. Second, we'll dive into engineering the perfect tilt. And finally, surviving nature and disasters. Let's just jump right in.
Section 1. The global high-speed fleet. Okay, to truly appreciate high-speed rail, we really need to understand the sheer scale and variety of the equipment operating worldwide right now. Because not all high-speed trains are built the same, mostly since the geographical and economic problems they're trying to solve are vastly different. Notice the distinctly shaped, 16-meter aerodynamic noses on the Shinkansen and global test fleets like the Fast-Tech 360. When Japan first pushed for commercial speeds of 360 to 400 kilometers per hour, they hit a literal wall of air. It created this massive sonic tunnel boom that sounded exactly like a shotgun going off. Obviously, you can't have that in a populated area. So to fix this, engineers used 3D computational fluid dynamics to stretch and optimize those noses. It is a perfect, beautiful visual representation of form following function.
But hey, aerodynamics is just one piece of the puzzle. Let's contrast how different nations balance speed with capacity. On one hand, you have the raw, sheer power of the German IC3, pushing 330 kilometers per hour just to rapidly move a few hundred passengers across Europe. But contrast that with Japan's Series 700 Shinkansen. Sure, it operates at a slightly lower 270 kilometers per hour on the Tokaido line, but it is basically a massive, high-density moving city, packing in over 1,300 people. South Korea's KTX hits that 300 km per hour sweet spot, but again, you see how the engineering priorities shift based on population density and network saturation.
Now, what's really fascinating here is how just a few centimeters can completely change the economics of your ticket. Energy consumption is a huge component of operating costs, right? Well, the French TGV Duplex utilizes a 3.91-meter bi-level width. This allows for double-decker seating, compared to the narrower 2.95-meter width of the German ICE. By safely fitting more people onto a wider trek gauge, they drastically reduce the operating cost per passenger. They aren't just engineering for speed, they are literally engineering for pure economic efficiency.
Section 2. Engineering the perfect tilt. Let's face it, designing a train to go fast in a straight line is relatively easy. The real challenge is navigating our winding Earth at 300 kilometers per hour without spilling everyone's coffee.
Our invisible enemy here is centrifugal force. A high-speed train hitting a curve at top speed is essentially fighting to stay grounded against the laws of physics. It's that apparent outward force drawing a rotating body away from the center of rotation. Without mitigating this force, you are forced to either drastically drop speeds at every single bend, which completely kills your timetable, or subject your passengers to some severe motion sickness.
Engineers solved this massive headache with tilting technology. But what's amazing is how they split into two wildly different philosophies to do it. You have natural tilting, championed by Spain's Talgo system, versus forced tilting, famously used by Italy's Pendolino system developed by Fiat. One uses the laws of gravity to its advantage in a totally passive way, while the other uses highly reactive computer-controlled hydraulics.
So the crucial point with the Talgo system is how brilliantly it tricks gravity. Instead of fighting the curve, the Talgo essentially elevates the car's support levels. By putting the pivot point high up, the car body swings naturally inwards during a curve, just like a pendulum. And because it uses centrifugal force itself to create the tilt, it is completely reliable, incredibly comfortable, and has a very low functional and maintenance cost. The result? These trains can navigate existing curves up to 25% faster than conventional trains. That is a massive speed upgrade without having to lay down billions of dollars of perfectly straight new track.
Then we have the sleek Pendolino, and this takes a totally different active approach. An onboard computer essentially reads the track geometry as it enters a curve and calculates the exact degree of hydraulic tilt required, actively leaning the train right into the turn. But here is an incredible engineering catch: the pantograph. That's the arm on top connecting the train to the overhead power lines. If the whole train tilts, that arm would rip right off the 25,000-volt wire.
So engineers had to design a mechanical compensation system to ensure the pantograph stays perfectly upright and connected, even while the car frame tilts dramatically beneath it. It's an absolute marvel to think about. All right, Section 3, Surviving Nature and Disasters. We've conquered physics, sure, but we are still very much at the mercy of the planet, and the safety margins at these speeds are razor thin.
I want you to remember this specific number, 40 gal. Gal is a unit of acceleration used in seismology. Over in Japan, which is obviously one of the most seismically active countries on Earth, 40 gal is the exact seismic acceleration threshold that triggers a network-wide emergency shutdown. If the Earth moves even a fraction of a hair above this limit, the system takes control completely out of the hands of human operators. And this brilliantly illustrates the URDAS protocol, the Urgent Earthquake Detection and Alarm System. Here's how it actually works, in 3 rapid-fire steps. First, seismographs stationed every 20 kilometers along the line detect the primary earthquake wave before the violent secondary shaking even reaches the tracks. Second, the system instantly and automatically shuts off the power supply to the substations. Third, the train's dynamic and mechanical brakes engage, bringing a multi-thousand-ton vehicle traveling at 300 kilometers per hour to a dead stop. Just think about the massive kinetic energy involved in halting your commute instantly during a tremor. This automated tripwire has literally saved countless lives.
But earthquakes aren't the only threat out there. The source material bluntly warns that a train's vulnerability to side winds increases dramatically with speed. If a side wind hits a train at 100 kilometers per hour, it's just a nuisance. If it hits a train at 350 kilometers per hour, now it's a critical stability threat. This wind doesn't just push the train, it violently whips those overhead catenary lines. To survive this, engineers actually have to massively increase the mechanical tension on those overhead wires, pulling them incredibly taut so they don't sway and break the power connection during high-speed, high-wind operations. And then, of course, there is winter. You know you cannot just cancel all the trains because of a little snow. The Shinkansen utilizes a whole suite of clever engineering workarounds to keep these aerodynamic bullets operational during brutal snowstorms. They use trackside sprinklers specifically calibrated to melt snow before it accumulates. The trains themselves basically wear the equivalent of a winter coat. Front skirt snowplows are built directly into the aerodynamic profile, and a body mount system hides all the delicate underfloor machinery inside the smooth outer shell, perfectly safe from the freeze.
So, we've seen how engineers mold 16-meter noses to defeat air pressure, how they trick gravity to tilt thousands of tons of steel, and build automated tripwires to outsmart earthquakes. But the pursuit of speed never really stops. So I'll leave you with this to think about. As global rail networks test operations pushing past 350 and even 400 kilometers per hour, what new, extreme, invisible forces will engineers have to conquer next? The battle between applied physics and transportation engineering is continuously evolving, and it is endlessly fascinating. Thank you so much for joining